Here's a diagram of a Conestoga wagon, and these were the type of wagons used in the 1800s, especially to haul very heavy loads. So you can see in this picture they're being hauled by oxen, which was generally the case. It required some pretty strong beast of burden to haul these very heavy loads that the Conestoga wagon was used for. Now I have to imagine, I wasn't around to see it, but being so heavy, these wagons must have got stuck in the mud on occasion. And when the wheels got stuck in the mud, that left the driver with a couple of options. One, get as many people as you can to get out and push and hope that that causes the wheel to come free from the mud. Another option would be stand here and then reach out and grab the wheel, and maybe grab the wheel as close to the top as you can. Maybe you grab hold of the spokes near the top of the wheel and then pull to try to get the wheel free from the mud. It turns out that creates a big difference in the friction force that appears where the wheel makes contact with the mud. So we'll come back and try to answer the question about the Conestoga wagon of where should you push, from behind or should you grab the wheel and pull. And we'll start with a slightly different investigation of a different sort of wheel, maybe a solid cylinder instead of a hoop. So let's draw that. So we'll say this is a solid disc. Maybe we can draw that in. And then we're going to apply a force at the top. And we'll just label our applied force as capital F. So there are a couple different spots that you could think of as the axis of rotation. So there's the point where our disc makes contact with the ground, and then there's another point at the center of mass. We know if this rolls without slipping, when rolling without slipping occurs, then the instantaneous velocity at the contact point is equal to 0. So let's see, what are some other forces we have to label here? Well, there's normal force. That's going to point up in that direction. And the normal force not only originates at the contact point, but it also passes through the center of mass. So whichever one of those points you might consider as the axis of rotation, normal force would be non-torque producing. Another force I have to draw in is mg. Now I'm going to draw the vector for mg just as long as the normal force, because I know those are going to tend to cancel one another out. So there's one remaining force. Other than the applied force F, the normal force N, and the gravitational force mg, there's a friction force. And I know where the friction force acts. The friction force acts at that contact point. My gut tells me to draw the friction force as a vector that points back in this direction. But all I really know for sure is it's a force that points parallel to the ground. So maybe the friction force points forward. I'm not so sure. So this remains a bit of a mystery. But here's the point. If I consider the contact with the ground to be my axis of rotation, then it doesn't matter whether the friction force points forward or backward. Either way, it's not a torque-producing force. So let's take a look at this. The net amount of torque when considering the contact point as the axis, well, mg is non-torque producing, friction is not torque producing, and normal force is not torque producing. So the only torque producing force is the applied force F. And it has a lever arm of what? What's the distance from the axis of rotation to the point where the force is applied? That would be 2r. They meet at a 90-degree angle, so our net torque is equal to 2fr sine of 90, so I won't bother writing that. Net torque can be substituted with I alpha, so I alpha is 2fr. Now, what are we going to substitute for I? Well, a solid disk has a rotational inertia about its center of mass equal to 1/2 mr squared. But we have a solid disk that's being rotated not about its center, but about the contact point. So we have to use the parallel axis theorem and say I equals ICM plus MD squared. So we've shifted the axis by a distance of r. So we just have 1/2 mr squared plus mr squared, and that gives us 3/2 mr squared. So there we go. 3/2 mr squared times alpha is equal to 2fr. I can cancel out one of these r's, and I get 3/2, and then what am I left with? M times the product of alpha and r, m alpha and r, is equal to 2f, or in other words, m times alpha r is equal to 4/3 f, where f means however hard the forces I'm applying. Maybe we imagine you pull with a force of 500 newtons to the right. Let's make it 600 newtons to make the math easy. So if you pulled with 600 newtons, then you'd get, well, wait a minute, what's this? Alpha times r. If we're assuming that this disk rolls without slipping, then not only does the speed of the center of mass equal the angular speed times the radius of the disk, but the acceleration of the center of mass equals the angular acceleration times the radius. So I can actually say this is ma equals 4/3 f. But we know what ma is. Ma, by Newton's second law, is net force. So there's a net force of 4/3 f. That means if I pull with a force of 600 newtons, that's just one of the multiple forces that acts on this object. The net force would be 4/3 of that. So let's see, mental math. 1/3 of 600 would be 200, and then 200 times 4 would be 800. So there's a mystery, huh? You're pulling with 600 newtons, yet you get 800 newtons of net force. That must mean that the friction force points forward and is equal to 200 newtons. So my gut had it wrong. I assumed I should draw the friction force as a vector that points that way, but actually the friction force must point forward. So if it does, then we have a free body diagram that just says two forces pulling forward, applied force plus friction force, provide for our net force. So the net force is the applied force plus friction. So ma equals applied force plus friction. So if I equate these two, if the applied force plus the friction force has to equal 4/3 of the applied force, then that must mean the friction force is 1/3 of the applied force. So I made up an example where the applied force happened to be 600 newtons, and then sure enough the friction force added to that with a force of 200, but I can make up any example, right? There's example number 1. Let's do example number 2, where the applied force is 1,000 newtons. Well, then that means the friction force points forward with a value of 333 newtons. All right, well, what if we had the same wheel or the same solid disk Well, that was interesting. And we find a way to put a handle on it, right? Some sort of axle that sticks out. And so instead of pulling from the top, what if we found a way to apply our force at the center of mass? Apply our force along the handle, along this axle. Okay, well then again, I've got some other forces I need to draw. For example, mg, n, and then friction. Once again, we're a bit stuck, aren't we? I know friction acts at the contact point, but I don't know whether it points forward or backward. Okay, so then let's let the contact point be the axis of rotation, then it won't matter. Either way, the friction would be non-torque producing along with the normal force and the mg force. So our only torque producing force is F, this time with a lever arm of R, not 2R. So our net torque would just be Fr. And we know that net torque is I alpha. And we know that the rotational inertia about this axis is equal to, same thing we had earlier, 3/2 mr squared. So 3/2 mr squared alpha equals Fr. I cancel one of the r's, and I have m times alpha r is equal to 2/3 F. But alpha r is the acceleration of the center of mass, so we have ma equals 2/3 F, but ma means net force. So the net force is only 2/3 of the applied force. So for example, once again, if we say the applied force happens to be 600 newtons, then you have a net force of only 400 newtons. And we know that the normal force and mg don't contribute to the net force because they cancel each other out. So the only other force that's factoring into the net force is friction. So for the net force to be less than the applied force, the friction force must point back in this direction. And in this case, it must have a value of 200 newtons. So if you were to try to pull a solid disc out of the mud, for example, you'd be much better off to apply your 600 Newton force at the top of the wheel as opposed to push on the handles, because the effect is friction will assist you and aid you and point forward, and even though you're only applying 600 newtons of force, you'd benefit from 800 newtons of net force. But if you were to apply that 600 newtons of force along the handles, then the friction force would oppose your effort and you'd be left with a net force less than your applied force. So what does this tell us about the Conestoga wagon? Well, that's just a different shape. So let's consider two cases. Case number one. Case number one is the situation where you get out of the wagon and you act like this guy and you pull on the spokes near the top of the wheel. So you give an applied force located at that point. Case number two, you get out and push from behind. Well, the way that force is transmitted, when you push from behind, all of your force is transmitted to the chassis of your wagon, and then that's transmitted into the axle, and then that transmits the force forward on the wheel at the wheel's center of mass. So by getting out and pushing from behind, effectively you're applying your force from the center of mass. So in each of these cases, I'd like you to try to figure out what's the net torque, and therefore, from that, figure out what's the friction force, both in magnitude and in direction. I think if you go through a similar exercise as we did for the solid cylinder, and by the way, the wheels on a Conestoga wagon are not solid discs or solid cylinders, they're hoops or rings. and so they have a different formula for calculating the rotational inertia. So take that into account as you attempt to solve this problem two ways. Once, when the force is applied near the top, and again, when the force is applied at the center of mass.